Welcome to determining the form of the rate law. So let's look at an example reaction. So we have ammonium reacting with nitrite, NO2 minus. Ammonium plus nitrite react to give us nitrogen gas, N2, and water, 2H2O. And so now let's write our rate law. We can say that rate is equal to negative the change in concentration of ammonium divided by the change in time. And we also know that that equals K, our rate constant, times the concentration of ammonium to some power N that we don't know, times the concentration of nitrite to some power M that we also don't know. So we need to determine the order of the reaction with respect to ammonium and to the nitrite. That is, we need to determine what N and M are. So remember that we need to determine these experimentally. We can't do this just by looking at the reaction. So we need some data from some experiment. So let's pretend that I've done an experiment, and let's say I've done 3 trials where I varied the initial ammonium concentration and the initial nitrite concentration, and I measure the initial rate of the reaction. Now if we compare the ratios for the rate laws for trials 2 and 1, so again I'll go back, and trial 2 was this one, the one in the middle, and trial 1 was that one. So you can see that the rate here doubled in going from 1 to 2. We've doubled from 1.35 times 10 to the minus 7 to 2.70 times 10 to the minus 7. And let's see what we changed. We kept the initial ammonium concentration the same, but we doubled the nitrite concentration. So doubling the nitrite concentration causes the initial rate to double. So if we take rate 2 divided by rate 1, we're going to calculate this fraction. So rate 2 over rate 1, well, we know that the rate was equal to K times the ammonium concentration to some power N times the nitrite concentration to some power M. So now note that in putting in the subscript 2 for the rate, I'm going to put in a subscript 2 for the concentration of ammonia and a subscript 2 for the concentration of nitrite. So we have the equation for the rate law with rate 2, with trial 2, divided by the rate and the concentrations for trial 1. Again, make sure that you put in this N and M there. So we know that the rate for the second trial was 2.70 times 10 to the minus 7 moles per liter per second, or molar per second. And we know that we're dividing that by 1.35 times 10 to the minus 7 molar per second. So our units there will cancel here. And this fraction, of course, simplifies to just 2. So we have 2 is equal to K times 0.100 molar to the N power times 0.0050 molar for the to the mth power. I've made a mistake here. Let's go back and look. It looks like I've taken the concentration from trial 1 and matched that with the rate from trial 2. So these two need to be flipped, because this fraction gives us 2, and when we flip this, now this side of the equation will also give us 2, because of course when we flip these two, then those will cancel, and the K here cancels as well. And so now we're left with, again, once we flip it, the 0.010 molar divided by 0.0050 molar. So we're left with 2 to the M on this side. So again, I've canceled out a bunch of stuff there. And we're left with 2 is equal to 2. Again, this should be flipped. So we have 2.00 is equal to 2.0 to the mth power. Well, the only way that that can be true is if m is equal to 1. So this means that now our reaction order with respect to NO2 minus the nitrite is 1. So we say this is, the reaction is first order with respect to nitrite. So if we then compare the ratios of the rate laws for trial 3 and trial 2, so again we're putting rate 3 with concentrations from trial 3 divided by rate from trial 2 and the concentrations from trial 2. Well, again, we've doubled the concentration, we've doubled the rate. Again, our units are going to cancel there, our Ks are going to cancel. Now, in this case, the ammonium concentration won't cancel, but the nitrite concentration will cancel, along with the mth power there. So now, we can figure out what this N is. And in this case, I've actually plugged in the concentrations in the correct places. And so now I have 2.00, because again, we've doubled our rate from 2.7 to 5.4 times 10 to minus 7 molar per second. And then here our molar cancels. And this fraction has a value of 2. It's still raised to the nth power. And now the only way that we can have 2 equal to 2 to the n is if n is equal to 1. So again, our reaction order is, with respect to ammonium, is 1. And so we say that the reaction is first order with respect to ammonium. So the overall reaction order is the sum of N and M and P and Q and so on if you have further reactants involved. So N plus M is 1 plus 1, which is 2. So the overall reaction is second order, but it's first order with respect to each of the reactants. So now we can calculate the value of our rate constant K. Again, remember we have rate is equal to K times concentration of ammonium to the nth power times concentration of nitrite to the mth power. And now we know that N and M are each 1. So if we want, we can rearrange this equation, solving for K. So we put K over on the left, and we get rate is equal to ammonium concentration to the N times nitrite concentration to the M. And now we can plug in some values. We know that N is 1. We know that M is 1. Here I've picked the values for trial 1. The rate for trial 1 is 1.35 times 10 to minus 7 molar per second. And the concentrations are 0.100 molar and 0.0050 molar. And then when we work that out, we get a value for K of 2.7 times 10 to the minus 4. Note here that our units then become liters per mole per second. That was determining the form of the rate law.